This is number 1 on the 4.5C homework. The question's asking the graph y is equal to x plus 3 over x minus 2. And it says to include any points of discontinuity, vertical, horizontal asymptotes, intercepts on all the legs. Okay. What I know about this one, if we start with domain, is x is not equal to 2. I know we're going to have a vertical asymptote at x is equal to 2. And I know we're going to have a horizontal asymptote. Well, if I follow the rule of leading coefficients, if the degrees are the same, and the degrees are the same here, then I get my horizontal asymptote should be y is equal to 1. Again, we always look at leading coefficients if the degree of the numerator is the same as the degree of the denominator. So I'm actually going to create a graph now that's going to match this. X is equal to 2, and y is equal to 1. And I can see that I've split the graph into 4 regions. So I have to have a piece on the left and a piece on the right. Well, I'm going to argue that this is very similar to the type of graph that we've already done. If I do the pattern, if I go with the long divide piece and try to get a remainder, what I end up with, if I long divide, then there's 1 times x minus 2. Close the signs, not the hearts of the deal, minus plus, and I get 5. So this is actually the same as 1 plus 5 over x minus 2. Well, that's y is equal to x, or 5 over x minus 2. That's 1. Now it's going to look a lot like the graph y is equal to 1 over x, just with a shift, a horizontal stretch, and a horizontal shift, a stretch, and a vertical shift. My horizontal stretch is 2. 1. Do transformation of base points, 1, 1, negative 1, negative 1 for y is equal to 1 over x. And those become 3 and 1 for x's. And stretch, multiply by 5 and add 1 is 6. Multiply by 5 and add 1 is negative 4. So I go 1, 2, 3, 4, 5, 6. Or sorry, 3, 6. So 3 up 6 is here. And 1, negative 4 is down here. Check for symmetry. Those look pretty symmetrical relative to those axes. One more thing I would probably want to do would be x and y intercepts. I'm going to do that over here because I can use this space since it won't be there. If I do the y-intercept, always easy to go back to the original equation. Y-intercept, plug in 0 for x, and I get 0 plus 3 over 0 minus 2, or negative 3 halves. So my y-intercept should be right here. I would expect 1 x-intercept, not 2, but 1. So let's go with 0 is equal to x plus 3 over x minus 2. Well, the wonderful thing about looking at x-intercepts from a rational function is that I can actually look at the original problem and know immediately what my x-intercept would be. X-intercepts are any value that makes your numerator equal to 0. Because then that would be 0 over something, and that would just be y equals 0. So I know immediately that that's x equals negative 3. Now, if you cross-multiply, you get the same thing. So that's where my x-intercept is. Then we swing that around. And this part should be pretty similar. And that's it.